Hi everyone, and welcome back. In our last lesson, we derived a formula for the equation of a plane in R3 that passes through some point P with coordinates say P1, P2, P3, and is perpendicular to some vector n, which we refer to as a normal vector for our plane. We saw that the plane could be described using dot products. It consists of all vectors x, y, z, such that that vector minus p vector is perpendicular to n. That gives us an equation like the one you see here. n1 times x minus p1 plus n2 times y minus p2 plus n3 times z minus p3 equals 0. That's the equation of our plane. This means that we can write down the equation of our plane provided that we know a point on the plane and a normal vector. Well, finding a point is usually not too difficult, but how do you go about finding a normal vector? Well, in this lesson we're going to learn how to do this, and we're going to use vector cross products. This lesson corresponds to section 10.4 of the textbook, so check it out for more information. Okay, let's try to unravel what we're actually trying to do. We are looking for a vector n that's perpendicular to our plane. The plane is just some set of vectors, right? So the question we want to answer is, how do we find a vector n that's orthogonal to a given set of vectors? Alright, rather than working with a ton of vectors all at once, let's suppose we have just two vectors, v and w. Can we find a vector that's perpendicular to both v and w? Well, it turns out we can. There are lots of vectors that will fit the bill, but this one that you see here, this complicated looking thing in R3, is a standard choice. We denote it by v cross w. The first entry is v2w3 minus v3w2. Notice that the first entries of v and w are not present here. In the second entry, we have v3w1 minus v1w3. Similarly, the second entries of v and w aren't present in this second entry. Finally, for the third entry, we have v1w2 minus v2w1. Not surprisingly, v3 and w3 aren't present here. As an exercise, I'd like you to verify that this crazy vector really is perpendicular to both v and w. You can check that using dot products. That is, this vector, v cross w, really does fit the bill. It's what we're looking for. We refer to this complicated vector as the cross product of v and w. And I'm going to give you an easier way to remember it on the next slide. For now though, let's try an example. Suppose I'm dealing with the vectors 1, 3, 4 and 2, 0, minus 1. According to our formula, the cross product of v and w is given by, well, v2w3 minus v3w2. So that's 3 times minus 1 minus 4 times 0. That's the first entry of our vector. For the second entry, we have v3w1 minus v1w3. So that's 4 times 2 minus 1 times minus 1. And finally, for our third entry, we have v1w2 minus v2w1. That's 1 times 0 minus 3 times 2. If you simplify this expression, you're left with the vector minus 3, 9, minus 6. And I'll let you check that this vector really is perpendicular to v and w. Pretty cool, huh? I have a few remarks for you regarding the cross product before we move on to some examples. So firstly, the cross product formula really does require you to have vectors with exactly 3 components. That's because the cross product is only defined for vectors in R3. The dot product we define for vectors in Rn, but the cross product is an R3 exclusive. Secondly, the dot product can be done in any order. If you do v dot w, that's the same as w dot v. For the cross product, not so much. The cross product switches signs if you swap the order of the vectors. V cross w is minus w cross v. Thirdly, if you know a little bit about determinants and you're looking for an easier way to remember this cross product formula, you can think of the cross product of these two vectors as the determinant of this 3 by 3 matrix. We put the entries of v in the second row, the entries of w in the third row, and in the first row we actually put our standard basis vectors. Now I know it's not maybe notationally correct to put vectors as entries of matrices, but we're going to do it here as a way to remember this formula. Now, if you'll recall for determinants, you can expand along any row or column, but your signs have to alternate. If you expand along the first row, for example, you're going to have a plus term, and then a minus term, and then a plus term. Whereas if you expand along the second row, you're going to have minus, plus, minus. I'll let you do a little review about determinants if you need to brush up. But for now, let's see what happens when we expand along the first row. I'm going to get I times, now I cover up the first column and first row, the determinant of this 2 by 2 matrix, determinant of V2W2, V3W3. As we move to the 1, 2 entry, we get minus J vector, and then we cover up the first row and second column, leaving us with the determinant of V1W1, V3W3. Finally, we switch signs again when we move to the 1, 3 entry. We get plus K vector, and we cover up the first row and last column, giving us the determinant of V1W1, V2W2. Okay, now I'm not going to expand all of these 2 by 2 matrices, but maybe we can just look at the first one. If you take the determinant of this 2 by 2 matrix here, you're going to do this crisscross thing. You get V2W3 minus V3W2, and we're multiplying that by I vector. This is exactly the first entry of the cross product from the last slide. So I think it's believable that this identity really does work out. Now you may remember back in linear algebra that if you switch the order of 2 rows of a matrix, the determinant is going to switch sign. Well, that might help to explain property number 2. If you switch the vectors v and w to w and then v, the cross product is going to switch signs. Our last property about cross products is an interesting one. It says that if you have vectors v and w, and you connect them up tip to tail like we did with vector addition to form this parallelogram, then the area of that parallelogram is equal to the length of your cross product vector. Pretty unusual, but definitely a cool property. Okay, let's see how we can use cross products to help us solve problems involving planes. Okay, in this example, I've given you 2 lines in R3. The first is parametrized by t, the second is parametrized by s. I want to find the scalar equation of this plane in R3 that contains both of my lines. Okay, we're being asked to find the equation of a plane. So we're going to need a point on the plane and its normal vector. Well, for a point, I suppose we could use any point on either of these lines, right? The lines sit inside the plane, so any point on the lines should be sufficient. But what about the normal vector? Well, let's think about this. If the normal vector is perpendicular to the plane, it must also be perpendicular to both of our lines. So if my yellow line is moving in this direction, and my pink line is moving in this direction, my normal vector has to be perpendicular to both of those direction vectors. Now this is starting to sound like a cross product problem. If we can find the 2 direction vectors, we could take their cross product to get the normal vector for the plane. And that's what we're going to do. So let's go ahead and look at this first line here. I'm going to rewrite this expression to look a little bit more like the formula for a line that we saw in the last video. I'm going to separate out the constant terms, giving me 3, 0, 2, and then I'm going to separate out the t terms. So I have plus t, and my coefficients here are 1, 1, 0. So from here you can see that 3, 0, 2 is a point on our line, and the direction vector is 1, 1, 0. We can now do something similar with our second line. If I separate out the constant terms, I get 2, 1, 1. That's a point on the line. If I separate out the s terms, I get plus s, 3, 0, 1. 3, 0, 1 is our direction vector. Okay, now we agreed that the normal vector should be perpendicular to both direction vectors. So I'm going to use the cross product. The normal vector is the cross product of 1, 1, 0 and 3, 0, 1. If I use my determinant formula, that's the determinant of I, j, k on the top row, and then I have 1, 1, 0 on the second row, 3, 0, 1 on the third row. Now you can expand along any row or column you like. I'm just going to go ahead and use the first row. So I'm going to get I times the determinant of 1, 0, 0, 1 minus j times the determinant of 1, 3, 0, 1, plus k times the determinant of 1, 3, 1, 0. Now I'm running out of room here, so let's go ahead and wrap up this example on the next slide. Okay, so I've got my lines up here at the top and my normal vector calculation down below. Here's where we left off. We need to take the determinants of these 2 by 2 matrices. The determinant of the first matrix is 1, so I have just I vector. The determinant of the second matrix is also 1, so minus j vector. Finally, for the determinant of the third matrix, I have 1 times 0 minus 1 times 3, that's minus 3. So minus 3 k vector. That gives me a normal vector of 1, minus 1, minus 3. And sure enough, it's perpendicular to both direction vectors. I'll let you check that. To wrap up this problem, we just need to write down the equation of the plane. Remember, the plane consists of all vectors such that n dot x minus p is equal to 0. Here, p can be any point on the plane. The lines sit inside the plane, right? So why don't we just take a point from one of the lines? Maybe 3, 0, 2. My plane equation is then given by 1 times x minus 3 minus 1 times y minus 0 minus 3 times z minus 2 is equal to 0. And there you go. There's our plane. As an exercise, I'd like you to think about the following problem. You know how if you have 2 points, that determines the equation of a line? Well, 3 points determines the equation of a plane. See if you can use ideas similar to those in the last example to find the equation of the plane passing through these 3 points. There's a question similar to this on your practice set. If you need any help, let me know.